Sure. Sure. No problem.
Good afternoon, everyone. I think we'll start. Welcome to the Wednesday Colloquium. We have a very timely and important topic today as a subject of the Colloquium, namely microplastics. Two developments recently has brought this into sharp focus. One was a Lancet report sort of highlighting the human health cost of microplastic. And the other was a UN Environment Program's intergovernmental negotiating committee's final set of negotiations, which happened in August, which is trying to greatly reduce the production of plastics. So what these recent developments have done is to shift the narratives about microplastics. So they are not only viewed as an environmental or ecologically harmful, but also has significant human health risk and significant economic costs. So to tell us more about this, we have Professor Guruswamy Kumaraswamy from IIT Bombay, and he's a prof at the chemical engineering department. His work focuses on structure property relations in soft materials, including plastics. After nearly 2 decades at NCL Pune, he joined IIT Bombay, where his research has increasingly turned towards questions of sustainability and the fate of materials at the end of the use life. In today's talk, he will share recent findings on how polymer molecular structure influences the way plastics degrade into micro and nanoplastics. So on a lighter note, Guru has a lot of friends here. I mean, he had significant overlap with a lot of people here. Amol is sitting here, Kedar, Mandar, and Shankar, and Guru are associated for longer, some 17 years association. So yeah, he's a friend. So Guru, all yours.
Thank you very much, Manoj. Okay, so can everyone hear me? Okay. So thanks, Manoj, for the very kind introduction and for the invitation to come speak at this Wednesday symposium. He also tells me that this is the longest running symposium series in the country. So delighted to be here. I've given technical talks before, but never a symposium. I'm not going to tell you about the harmful effects of microplastics, right? So let me just sort of put that up front. And part of that is because I have no idea what the harmful effects of microplastics are. They're potentially harmful. They're potentially harmful to the environment. They're potentially harmful to human health. And there's been a lot of recent studies, and I'll point to that. In fact, I keep saying that there is an entire cottage industry of researchers who've been finding microplastics in every conceivable bodily fluid. And I'll tell you about that as well. So the question is, what does that do? I don't know the answer to that. I'm not qualified to answer that, but I'm hoping that I can, maybe strike up some collaborations and have maybe some of our colleagues in biology take some of the microplastics that we produce and put them in organisms, in cells, and see what they do. Right? So my talk is really more about how microplastics form. Right? How do you go about getting these microplastics? And we've come up with ways by which you can make these microplastics in the laboratory that look like microplastics that you find in nature, in the environment. And that's really, I think, the key part I'm going to focus on is the processes by which plastics break up to give you microplastics. Because everybody has been looking at these model microplastics, which you can buy these very well defined 1 micron polystyrene beads. You can just order them off of Aldrich, but they are nothing like what real microplastics are. And that's the point I want to make to this talk today. So I'll focus more on what are the processes that give rise to microplastic formation and how do these molecules break up to give microplastics. So just as to start with, the reason we're worried about microplastics being everywhere is that plastics are everywhere, right? Whoops. Okay, so it's not changing here, but it's changing. Right, so let me try and get this to work slowly. So plastics are everywhere. And if you think about it, we are really unable to manage without plastics, right? From packaging, and packaging is ubiquitous. Amongst the largest uses for polymers, for plastics is really in flexible packaging, right? A staggering 40–50% of the plastics that we produce goes into packaging. But apart from that, it goes into a whole bunch of other things that you can see, right? To the point where if you think about our global annual production, that exceeds 400 million tons today. So every year we produce 400 million tons of material which are derived from petrochemically derived monomers for the large part. And if you look at this, polypropylene, various versions of polyethylene, just these two polymers, polyethylene and polypropylene, account for about 40–50% of all plastics produced, right? And this belongs to a class of polymers that are called semicrystalline polymers, and I'll talk briefly about that. But these are the big, right? Polypropylene, polyethylene, PET, the stuff that goes into bottles, polystyrene, and so on and so forth. So these are the big polymers that we produce in very, very large quantities. They go into a variety of applications, including packaging. Single-use plastic can be any of this. Typically, single-use plastic is packaging, right? So if you think about milk bags, right? So we all get our milk in milk pouches. But if you go back and think about the start of the white revolution, where we were starting to produce a large amount of milk, what limited you was the availability of glass bottles. Because when I was very, very young, milk came in glass bottles, and you had to exchange those glass bottles, and you had to transport heavy glass bottles using a lot of diesel for transportation. So when the first polymers came, polythene bags, these are typically LDP or linear low density or low density polyethylene bags, that really allowed people to get milk out to everyone. But then if I think about the polyethylene that's produced, you make this polyethylene, you make a milk bag out of it, you sell it to someone, next morning it's trash. And I'm an engineer, right? So if I look at the value of that material, I'm buying virgin polyethylene for about 100 rupees, a little more than 150 rupees a kilo. But the next morning, when I go take it to my raddiwala, even if I clean it up, the value comes down to about 25, 30 rupees a kilo. It's a huge reduction value. So that's a different problem. But the point I want to make here is that polymers are pervasive, and it's very difficult to get away from it. So I want to sort of go back, and some of you might know this movie. This is a 1960.
Come with me for a minute. I want to talk to you. Excuse us, Joanne.
Of course. Oh, he is such
It's just
a
incredible. I look at him and I can't believe it.
I know
I
it.
simply can't believe it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
And so, there is a great future in plastics, right? And in 1967 to today, you've gone from something like 15 million metric tons to what I told you today, 400 million metric tons. And the growth has been pretty much exponential. So if you were in the plastics industry as this guy was convincing Dustin Hoffman to get into. So Dustin Hoffman is visiting, he's just graduated from Yale, he's visiting home. Very interesting movie, The Graduate. But the thing that stuck to me was, what he's advising him to get into is plastics, because it's a growth industry, and we've grown enormously since that time. So, we're producing a large amount of plastic today. Now, where does that plastic go, right? So, so this is the system. This is us. This is the Earth. We are producing plastic, and so the production of plastic, this is data from 1950 to 2015, we produced about 8,300 million metric tons of plastic, right? At any given time, there's a small part of that is in use, and the vast majority of that, right, about 5,000 million metric tons, is just discarded. And now that can be discarded in well-managed waste dumps. It could be discarded in not so well-managed waste dumps. Some part of it is recycled, and one of the endeavors is that to keep the amount of material that we have fixed, because we are going to need to use plastic. Instead of making more plastic, can we recycle more? Can we not throw away as much? So that's another part of what I do in my lab. But what I'm going to be concerned about is this kind of plastic that's either discarded or that leaks out into the environment in a variety of different ways. And that could be things like plastic that we throw away, microplastics, and so on. And so, living in India, it's not unusual to see something like this, right? So I grew up in Chembur, right next to Govandi. Right? There's a huge waste dump out there. And you can see that plastics, amongst many other things, are thrown away and discarded in these kind of landfills. This is mismanaged waste. And when you have these plastics that go into landfills, they get acted upon by a variety of environmental factors. Or you could see them, for example, littering waterways. And one of the things people are very concerned about is the plastic that gets into oceans and into water. And so when you have plastics that are out there, they're subjected to, it's cutting off the top of my slide. I don't know if I can get rid of that. So when you have plastics that get discarded into the environment, then they're subjected to environmental attack. So for example, it could be subjected to hydrolysis if it's sitting in water, a variety of microbial or enzymatic attack, chemical attack, but also it's going to sit out in the sun. It's going to be exposed to UV. It's going to lead to oxidation. And that's one of the reasons why you add a lot of materials to plastic. So when we think about polyethylene or polypropylene or PET, never do we actually use plastics as it's made right out of the reactor. Before it gets to you, you put in a whole variety of small molecules that are used to stabilize this. So polypropylene, for example, will always have antioxidants, things that will promote how it's processed and so on and so forth. Right? So these are called additives, and they're a big part of what we don't know about what comes in the plastic that we use. No companies today are not required to disclose what they put into plastics that they use. And these things can leach out and cause problems as well. But they're required because they prevent you from being immediately subject to these kinds of UV and oxidative degradation. Apart from that, there's just mechanical wear, right? So for example, one of the biggest sources of fibers that get into the water supply, into the ocean, is through things like washing machines, right? So washing machines typically don't have filters that can trap fibers, right? So if I throw a polyester shirt in a washing machine, it will give off these small fibers, and these are also microplastics that will then get into the water supply and get into the ocean. The other big part of abrasion or mechanical wear-induced generation of microplastics is in what I call road dust. I don't think I talk about that here, but that's something that Shankar and I worked on for, we've been working on it for several years. We have a joint PhD student who works on it, which is if you take a vehicle and it runs on the road, it runs off of rubber tires. And when that runs on the road, you scrape off asphalt from the road, the rubber wears off. Every time you apply the brakes, there's the brake pad that contacts and gives off particles. All of this constitutes road dust. And about 80+% of terrestrial microplastics is actually road dust, right? And so that's something that to understand how these things form has been a big part of what Shankar and I have been doing. Now, what is this microplastic and nanoplastic that people are talking about? So turns out that there was no consistent definition in the literature. And the definitions for what a microplastic is really came from estimates of what is the smallest size of plastic that you can ingest, right? And so, for example, if I have any small piece of plastic like a bead that's less than 5 millimeters, fish can ingest it or other kinds of animals can ingest it, and that then gets into the food chain. And that's the reason that 5 millimeters was considered sort of a size. So today, the consensus is largely that anything greater than a micron, less than 5 millimeters is considered a microplastic. Anything smaller than that is considered a nanoplastic, right? So question that I'm going to focus on really is, what leads to the formation of these microplastics? And the reason I'm concerned about it, and this is the reason I think the Lancet report sort of speaks about this, people have recently been finding microplastics in all kinds of things, right? People have found it, for example, this is an NEGM paper that talks about presence of microplastics and nanoplastics in cardiovascular events and correlates the presence of microplastics to cardiovascular events. It's a relatively small study, about 200 patients, and it does show that there is a positive correlation between the presence of microplastics and cardiovascular events, but it's a very small sample size. So as of now, if you ask me what is the health implication, potentially adverse, but I don't know. I think we don't yet know all of that as yet, right? Yeah.
The mechanism, like is the microplastic going through your bloodstream into your heart, or is it just some correlation with the...
At this point, this is a correlation. I don't think there is a mechanistic understanding of that. So they've also correlated, say, for example, microplastics have been found to cross the blood-brain barrier, and they found it in brain tissue. Is there a correlation with neurodegenerative diseases? Is there plaque formation as a consequence of microplastics? I don't think the answers to that are there yet, which is the reason I'm saying I don't know if there's an adverse effect. So just as an aside, people have also found that when you have microplastics that, for example, you ingest and gets into your bloodstream, it gets coated by all kinds of proteins that agglomerate on the microplastic, and then maybe the body just looks at it as something which is decorated with protein. So we don't yet know is the short answer. I mean, and this is outside of what I'm an expert on, but as of now, there are indications that you find them everywhere. These are foreign material, so potentially they're not necessarily good for us. but I don't know if that's conclusive as of yet.
And does the body or any living organism have any mechanism to physically break these into even smaller pieces, or that it's once it enters, it's like...
So I'll speak to some extent about that. So microbial attack. So for example, for some kinds of polymers, that's possible. So polyethylene and polypropylene have only carbon-carbon bonds along the backbone. That's very difficult to do very much with. But for example, if I have a polyester, right? So there are esterases that we have that could break these down. And so one of the things people are trying to do is to recycle PET, which is a polyester, by breaking it down into the original alcohol and acid, and then go back and repolymerize it and make this fresh again. But for things like polyethylene and polypropylene, especially because of the fact that they form crystalline objects, this is very unlikely that we will be able to break them down using enzymatic attack. Right. So today's talk is largely going to be about end of life of plastics. My research, like I said, is very gloomy. It looks at end of life, but specifically it looks at end of life of plastics. I also work a lot on extending end of life. For example, I talked to you about the recycle loop. So can we recycle plastics? These are 3D printed objects made using filament, which comes from used Harpic bottles. So this is actually Harpic bottles that we collected from the rag pickers in Pune, and then came up with an additive-based method.
Guru, when you say
Yes.
end of life, does that mean that it can be recycled, or I mean?
Yeah.
What does that mean? I mean,
Yeah. So let me go back. So if I think about what does plastic mean? The word plastic comes from thermoplastic. So thermoplastic means I can melt it and reform it. Now the useful properties of plastics come from the fact that these are extremely long chains that are connected. I've already told you that plastics are susceptible to attack, right? And that's also true in terms of taking these plastics up to high temperature when you recycle them. For example, if you just melt them and recycle them, you'll have to go to the melting point, which is typically 200, 250 Celsius and so on. Now there, even thermally, you can have bond cleavage. And what that means is that polymer becomes less useful. So in our country, we have an amazing ecosystem to recycle PET. So there's the practical aspects of it, which is, can it be collected? Can it be collected cheaply? Can it be done in large enough quantity that you can recycle it? And there's the technology aspects of, what does it do? Can you get the same kind of properties? Now, in our country, we collect about 90 to 95% of all the PET bottles that we use. So today we use worldwide over 8 billion PET bottles. So more than one PET bottle per person per year, right? Now, in our country, we can collect all those PET bottles. But what we do with the PET bottles is we melt it and we make fiber that goes into T-shirts that cricketers wear or football players wear and so on. Now that is a lower grade of plastic because you don't do bottle to bottle. In Europe, you can do bottle to bottle because you put in an additive that prevents the chain from going to lower molecular weights. But over time, that adds up defects. And what's happened now is some of the bottles in Europe are non-recyclable because there's so much of this additive in there. So yes, there is a possibility, but it is, the technology is challenging. It is in principle possible. Yes. Yeah, so where do you take it out of the body, right? In this case, if you're finding this in brain tissue or in tissues that in other kinds of, like for example in the heart and so on, the question is how does it get there and how does one get it out, right? So taking it out of the body is, I think, very challenging. Yeah, so this is not an equilibrium concentration. So thermodynamics doesn't play a role here. These are simply suspended in the blood, and there is no equilibrium concentration in the blood such that we can take them out. But yeah, so my feeling is that mitigation strategies need to focus more on something that the UNEP, but unfortunately the UNEP meeting on recycling plastics or reducing use of plastics was a failure. They could not get to an agreement, and including people like India who, we voted against some of those arguments because it does not make sense for a developing economy to say we'll curb plastic, but everybody else can keep using plastic. So we had to somehow figure out ways by which maybe we don't have to use as much plastic, right? or use plastics that are particularly hard to recycle, like multi-layer plastics and so on. But can we clean them up from our body? I don't think there's an easy way of doing that. Right? Of course, is it implicated in something? That again, I don't know. But maybe if it is, then from those organs, we'll have to find ways of cleaning it up. Okay. Yeah. So let me give you before we get into all of this, so let me sort of give you a very brief description of what plastics are, why they're useful, and what makes them useful. So polymers or plastics are long molecules. Plastics are polymers that can be thermally reprocessed. So I can take it, melt it, reform it, melt it again, reform it. But again, there's always going to be some kind of a breakage of the chain size as that does it. Now, the reason polymers are so useful and the fact that they've grown to this 400 million tons per annum kind of usage is because of what I call polymerness, right? The fact that you get this extremely long chains gives you topological connectivity along the chains. Chains can't cross each other. And that gives rise to a variety of properties that make polymers extremely useful, just physical, including mechanical properties and other kind of physical properties. One of the things that people didn't believe until just about 70, 80 years ago is that a polymer is a single molecule, because the size of these molecules can be gigantic. Commercial polymers will be easily 100,000 molecular weight, or sometimes even, for example, polymers that go into hip implants or things like that, right? Ultra high molecular weight polyethylenes can be of the order of a few million molecular weight, right? One single molecule. And so if you have such a large molecule, then the spatial extent is also very, very large, tends to maybe even 100 nanometers in size. And the fact that they are connected objects make them absolutely fascinating objects to study the physics of, because the physics of the polymer now is not governed by the details of the chemistry. So it's a polyethylene or a polypropylene or a polystyrene or PET or any of these molecules that I spoke to you about. If it's a flexible polymer, then you can see for a wide variety of polymers, this is the viscosity on a log scale versus the molecular weight. All these polymers follow the exact same trend, and that comes about because of the fact that they are connected objects. So if you have strings, then if strings cannot intersect, then they will form entanglements, and that entanglements will give you a scaling that says that, the polymer viscosity scales with the molecular weight. Why do I point to that? Because this tells you why the molecular weight is so important. So if I take a chain and I break it by a factor of 2, right? I cut it, my average molecular weight goes down by a factor of 2, my viscosity goes down by a factor of 10. It becomes that much less useful. So the molecular weight is an extremely important attribute for the polymer, and preserving that molecular weight is important in terms of the applications of this material. And so mechanical properties depend on that. Sorry, Amol. Yes. So this is why Dejean got his Nobel Prize. Yes.
I meant to ask something. Index is changing, no?
Yeah. So each polymer, depending on the detailed molecular structure of the polymer, has a certain degree of stiffness, and so that stiffness determines the length beyond which polymers can start to entangle with each other. So there is something called a persistence length, which tells you that if I look along the bond, how long does the bond orientation persist in space? And where do you sort of lose that bond, the correlation between bond directions? So that gives you something called a persistence length. And when you go beyond that, at some point, the polymers get long enough that they're flexible enough that they can start entangling with each other. So the point at which they entangle, the viscosity, so if you don't entangle, so what is the viscosity? Viscosity is effectively a measure of the time scale for stress relaxation. So if I take the polymer chain and it's sort of like a small molecule, it sort of wiggles and relaxes stress. But if I go beyond entanglement, I can't wiggle because I can't go through bonds. It's Pauli exclusion. So the only way I can relax stress is to diffuse out in and out of those bonds. So that's a different mode of relaxation, and that gives you this 3.4 power. And that's the physics that gives you this 3.4 power.
So you're also saying the viscosity mentioned here is not the fluid dynamics concept of viscosity.
It is. It is. The fluid dynamics concept of viscosity tells you about if I take, let's say, whatever, water or something, some kind. So these are non-Newtonian, right? So everything that we talk about are, we typically think of Newtonian viscosity. Polymers are not Newtonian, and they are also what are called viscoelastic materials. So they're the worst kind. They're non-linear viscoelastic materials. But that's something I don't want to get into right now. I just want to make the point that the molecular weight is important.
Okay, I'm sorry for one
Sure.
more. when you have non-Newtonian fluids, you don't have a single viscosity, right? It's a non-linear.
The viscosity then depends on shear rate.
Okay.
But the other way of thinking about it is the viscosity depends on the time scale over which you're measuring that, and which is sort of what the point I wanted in the case. Is there another question? Right. So that's polymers, right? Long molecules, the molecular weight is extremely important. But now I told you that, not all the polymers that we are particularly interested in, things like polyethylene, polypropylene, PET, these are polymers that are crystallizable. Not all polymers can crystallize, right? And so if I think about polyethylene, what allows it to crystallize is the fact that you get this decrease in free energy because of van der Waals interaction when these chains pack with each other. So for chains to pack with each other, they need to be extremely regular, which means, so let me take something that looks like this. So this is, the blue is a methyl group. So let me, right? So this is just polypropylene, right? So I've got a carbon chain, and so these are all hydrogens. Where I don't draw this is a hydrogen. Right? So this methyl group is what I'm pointing to here. Now, if I take the backbone and I stretch it out to make it all trans, the methyl groups can be all on one side, or they can be exactly alternating. And this is not something I can do by rotating bonds. This is fixed. I've already extended the chains to be all trans. So I can either have all the methyl groups on one side or the methyl groups alternating, or completely random. And how you make this depends on the catalyst chemistry. The only useful polypropylenes that one makes are what are called isotactic polypropylene. This is the polypropylene that we buy in large quantities, and all the 100 million tons of polypropylene that we're talking about is all made using the catalyst that gives you this. So once you have materials that look like this, then they can actually crystallize to form ordered structures. And so polyethylene, isotactic polypropylene, but not atactic. If I get atactic polypropylene, exact same chemistry, right? It's a CH2, CH3, right? The exact same chemistry, but it cannot crystallize. Polystyrene, on the other hand, is a material which is stiff at room temperature. So it's what's called a glassy polymer, and I won't go into the details of that. But the commercially used polystyrene is atactic polystyrene. You can make syntactic polystyrene, which can crystallize, but we don't use it commercially. Okay, so the yellow, what is highlighted yellow are the materials that are commercially available. These are semicrystalline, these are not. Okay. And so when you look at how these things order, when you take these polymer chains, they're very, very long objects. They're so long that the time taken to take a single polymer chain, which is all folded up and it's coiled, and to stretch it out is unreasonably long, longer than the time of the universe, right? And so what happens is when these things want to crystallize, they will locally form rigid segments. Those rigid segments will pack together to form these kinds of crystalline objects, right? These are what are called lamellae. They are crystals, and these are about tens of nanometers in size. But if you remember, what I told you is that a polymer chain can be hundreds of nanometers in size, right? Which means a single polymer chain will span many of these crystals. And that's what makes the polymers so interesting, because they're crystalline and they're rigid, but because of these connectors, they're also very ductile. And so these chains, called tie chains, are the things that tie these crystals together and make the polymers have interesting mechanical properties. Okay, and that's the reason semicrystalline polymers account for very large percentage of the polymers the plastics that we currently use. Okay, so that's semicrystalline polymers. So you can have polymers that are semicrystalline. You can also have polymers that are not crystalline. And the question that we started asking some time ago was, how does this kind of crystalline order affect the formation of micro and nanoplastics? Is there a difference? Because most of the plastics that we use are semicrystalline. Not all of them are, but does that make a big difference in terms of how these micro nanoplastics form? So the question is really about mechanistic insights into how the structure gives rise to these microplastics. And so because we can get access to materials that are not commercial, so we looked at comparing atactic polypropylene that cannot crystallize with isotactic polypropylene. This is commercial and it can crystallize. Atactic polystyrene, which is commercial but cannot crystallize, with syntactic polystyrene, again, which we can get, but this can crystallize, this cannot. So the chemistry is matched, right? So in terms of chemical attack, it should be the same, but then the stereo regularity determines whether or not it can crystallize. And also PET, but I'm not going to talk about
against those plastic names. What have you put in brackets?
this.
Companies that they.
Oh yeah, sorry. This is where I buy it from. So it's atactic nobody makes, and I bought it from Sigma Aldrich. This is from Reliance. This is from a company called Supreme, which is an Indian company. Idemitsu makes. So they have a pilot plant that makes small quantities of syntactic polystyrene, but there's nobody who uses this commercially, at least to the best of my knowledge. Right? Okay. And so how do you do this, right? So typically, if I worry about microplastics that are left out in a garbage dump, so they are under quiescent conditions. I'm not worried about mechanical abrasion, but I'm looking at something that's sitting out in a garbage dump and being exposed to UV and solar radiation. And that will take 5, 10 years, maybe longer. So if you've had, for example, a plastic chair that you left out in your garden or out in the sun for a very long time, you'll come back and after 5 years, you sit on it, it'll break, becomes brittle, right? But my PhD students were not willing to wait that long. And so we had to come up with an accelerated aging protocol to try and replicate what happens in the environment, but do it at a reasonable time scale. And so we used a little bit of chemistry. We take a potassium persulfate aqueous solution, and if you heat it up, it dissociates to give you all these radicals, which are, so the alternative to this was something called a piranha etch, right? So there's actually something in chemistry where you can take a solution with peroxide and acid, and if you heat it up, it gives you what's called a piranha solution because it just chews up everything you put inside. So similarly, we use this persulfate etch, and this is something that we know from people who work on water pollution, right? So people who look at ways of remediating polluted water will do all these kinds of treatments to clean up all the organics from it. And so we adopted that protocol and made polymer films and subjected them to this kind of attack through these free radicals and asked the question, what happens to these films, right? How do they fragment? Do they give you microplastics and so on and so forth? With PET, we adopted a different method. This is an ester, so I can simply hydrolyze it. So you take it in an autoclave at 110 Celsius and you just sort of cook it until it falls apart. But I'm going to show you results on polypropylene and polystyrene, which is using this particular chemistry. The results are qualitatively similar to what we see with PET. Okay, so first thing, right? So I'm taking this film, I'm putting it into this solution which has this persulfate, I etch it at this temperature, and then I take the water and I ask the question, does it scatter light, right? Because if it has particles in it, it should scatter light. And so this tells me the scattering counts, and this is data for syntactic polystyrene, this is for atactic polystyrene, this is for isotactic polypropylene, this is for atactic. So notice that these two things which give you much less scattering are the amorphous polymers that do not crystallize, while the ones that do scatter a lot, that give you a lot of particles, are the crystalline polymers, right? Why is that the case? This was a non-intuitive kind of a finding, and so we were very surprised when we saw that, right? I'm going to just tell you what happens on day 0. This is the scattered intensity from the crystalline polymers is much greater than what you see from the amorphous polymers, right? But then you take these out and then continue to degrade them. I'll come back and talk to you about this later. And what you see is that if you continue to degrade them, this amorphous polymers, the scattering from them comes down even further to almost the level of what you see from water. But for polymers that have crystals in there, those particles persist and continue to scatter even when you etch it using this nasty piranha kind of etch over a long period of time. So what this tells you is, at least for these crystalline polymers, if you generate particles and those particles stay in the environment for a really, really long time, despite continuing to etch these things over time. What's scattering of light? This is visible radiation. So if I just shine laser light through this, how much light is scattered from there? This is scattering at, I think, 15 degrees or something like that. So this is just, so long as you have any kind of variation in the refractive index in a system, you're going to get scattering. We're just picking up that using the intensity of scattered light. Right. So now we went back and looked at the stuff in water. So I have particles. What do those particles look like? Why do the amorphous polymers not scatter? And so this is SEM data this is for isotactic polypropylene. This is for syntactic polystyrene. So two different chemistries. Both of these are crystalline. And what you see is you can very clearly identify that there are particles in there, right? For atactic materials, these are the materials that do not form crystals, what you see is the formation of something that look like oily droplets, right? So these appear to be oligomeric, oily materials, residues that come from taking these big chains, chopping them up, but you don't get particles, you get liquid in these systems. Why is that interesting? We'll come back and talk about that. A lot of this stuff, suppose I put this in soil, right? If I have materials that form particles, and these are crystalline particles, so these are not really susceptible to enzymatic attack. They're not susceptible to microbial remediation. But if I have things that, for example, form these kind of oily droplets, then it's possible that there could be microbial remediation of this. So for example, if you go to a car garage, right, and you look at people who spill motor oil around that, and you dig up the bugs around there, you'll find that those have now evolved to the point that they can use the motor oil as a carbon source. And so if you have materials that are oily, then it is possible to do that. I'm not claiming that this is going to happen, but I'm saying that there is a possibility. The problem with particles is they're not really going to be susceptible to attack because it's very difficult to etch something that is so tightly packed together. Yes, in both cases, for atactic polystyrene and atactic polypropylene. Okay, so what really happens here, right? So what's happening here is if I now look at these materials, so this is now as a function of time. This is data for isotactic polypropylene, syntactic polystyrene. These are the ones that do give you scattering. And I look at the scattered intensity. What I notice is that when I put this film in there, I put the film and just keep watching this thing as it evolves. Initially, I don't get any particles. But there is sort of a critical time, some kind of an induction time. And beyond that induction time, I see the formation of these particles. This is also true for PET using a different chemistry, hydrolysis, to break it up. There is an induction time and then it takes off. And it looks like this induction time correlates with the time taken for the material to become brittle. What I'm plotting here is a stress strain plot, when I'm taking the maximum stress that gives me the strength of the material. So this is the strength of the material, and as the strength of the material decreases is when I see this induction time in the formation of these microplastics. So, the induction time really comes from the point at which these films become so brittle that they start falling apart, and it correlates with the strength decreasing dramatically in this system. This is something I sort of alluded to earlier, is that as these things continue to degrade, effectively, you get these crystals. Now, these crystals, I told you, form these sheets, lamellar sheets. You basically get these crystalline sheets, and over time, you break off the connections between the sheets. You break off the tie molecules, and eventually, you end up with only these sheets. I'm not going to go into why they are log non distributed. It just comes from the fact that I won't go into that. But eventually, what you see is you end up with essentially single layers of these sheets, which are crystalline, and you can then look at electron diffraction to really see that these are crystalline objects that you get in here. Okay, and so this is really the mechanism that we see, is that if you take these polymers that can crystallize, the crystals form these sheet-like structures. These are tens of nanometers in size. They're connected by these tie chains. And over time, you can go and if you expose it to, say, free radical attack or oxidation, it starts breaking these tie chains, and that gives rise to these particles, and these particles persist in the environment, and these are, pretty much impossible to degrade over any reasonable period of time. So that's the first part of my story. I'm already running late, so let me do the following. So there's one bit that tells you the difference between polyethylene and polypropylene. That's where chemistry becomes important. It's not just the physics of the long chains. But let me very quickly tell you about one last problem. Skip this and tell you about this stuff which, hey, Shankar, you're wearing the same shirt today. And so this is about terrestrial microplastics or road dust. And this is, I told you, right, 80 to 90% of all the terrestrial microplastics we form are things that come from breakup of these tires. And so this is what we did. Initially, I had a master's student who was jointly advised by me and Shankar. And then Smita and Anit finished up these experiments. So we took a tire, we mounted it on, so we didn't want to worry about asphalt coming off and so on. So we mounted it on a metal wheel. So it sort of looks like this. So it's a metal wheel. This kind of pattern is what you see on concrete roads. And so we ran the tire on it. That's very clever, right? So what they came up with is basically an EV retrofit kit. You can just buy off of Amazon a DC motor that will plug into this and run this tire. And you can control it, change speeds and so on. And then Anit built a thing where you can change the normal load. So it's like the weight of the person sitting on it. And we looked at the particles that came off, the large particles that just deposited, and then the smaller particles that we could check using an aerosol counter. And the data sort of looks like this, right? So you turn on the tire, you see a huge spike in the number of the particles that come off. And then when you turn off the tire, there's a small relaxation of the plastics. It's all enclosed in this big chamber to make sure it's all clean to begin with. And so the key result, and I just want to sort of give you this one key result, is that if you look at the particles that come off, and this is something that people hadn't seen earlier, there's two distinct kinds of the particles that come off. Particles that are large and that settle down form this distribution, which is a log normal distribution, similar to what we saw earlier. That really just comes from the central limit theorem. You take something, you keep fragmenting it, eventually the distribution has to be log normal. And so that's what you see. This is sequential fragmentation that you get in the structure. But there's another set of particles that give you something that looks like a power law, right? And this is true as you increase the speed. It's true as you increase the weight of the particles. What you see is that as you increase the speed of the weight, the large particles that come off, and these are the particles that are PM10, right? These are the particles that you can measure the weight of. Those particles don't change at all. What changes is the really small particles that stay suspended, the really small particles that that do not settle and that we breathe in. And those are extremely dependent on the weight and the speed. The higher the weight of the car, which means if you go from IC engines to electric vehicles, there's no pollution because you're not burning carbon dioxide, you're not burning carbon-based fuels, but you're generating a lot more of these particulates, and those are things that go into the environment that we are not currently measuring and that we breathe in. Yeah, so this is in millimeters. So this is 300 nanometers to 10 microns. And this is millimeters. So this is on a log scale. Okay, so I'm going to stop here since I'm sort of out of time. I just don't want to leave you with this. So we are not going to go away from plastics in my lifetime, I don't think, right? We are just too dependent on them. Can we minimize our use of plastic? And that's something that the UNEP committee is considering, saying, can we reduce the per capita usage of plastics? Currently, it's very unequal. Our per capita usage of plastics is very different from what it is in, for example, the United States. And so is there sort of an equitable way by which you can reduce that? But because they're soft materials, they're easy to process, they have really attractive mechanical properties, that makes them extremely versatile. And that's the reason we use a large part of this. Now, a large part of the plastics that we use, 70+%, are semicrystalline, and 40 to 50% is just polyethylene and polypropylene. Now, the part I didn't tell you about is it seems like polyethylene is much better than polypropylene for reasons that we are just starting to understand. I didn't have time to cover that. But the problem is, while we think of these plastics as indestructible, they're not. They are susceptible to chemical attack, they're susceptible to radical attack, they're susceptible to hydrolysis. And because of that, they become brittle and they fragment. And that gives rise to micro and nanoplastics. I have no ideas on how to mitigate this, right? I mean, once you have, so in the bad old days, so these are all what are called secondary microplastics. Primary microplastics are microplastics that we intentionally produce and put into products. And we used to do that, right? Even until 15 years ago, face scrubs used to have polyethylene particles that were used as abrasives, so that you can clean your face better and so. We've stopped doing that because that is polyethylene particles that you wash off, that goes into the storm drains and eventually goes into the ocean. There is no filtration mechanism that's possible to pick up these small particles when you do, wastewater processing and so on. Right? We have stopped doing that for the most part. There's sort of the ban in India is really through the BIS and not through other bans. So there's sort of questionable legal validity in India, but in other countries, it's actually banned. So the point I want to leave you with is that if you're looking at quiescent fragmentation, which is just letting it sit out there and bake under the sun, then there seem to be very big differences between semicrystalline and amorphous plastics. They seem to break down in very different ways. And that has important implications for, what kind of microplastics we produce. We spoke very briefly about rubbers. So tire wear, we produce about of the order of, I think, 1 million kgs of million tons of rubber that goes into tire in our country alone. And there's a lot of that gets worn out, and that stuff goes into particles that deposit on the road. Some of that gets washed off in our monsoon and goes into the ocean, and fish eat it. I'm less worried about that than I'm worried about the stuff that I'm breathing, right? And that's a really big problem, and that's something that people hadn't seen before. And Shankar and our paper was really the first to sort of highlight some of these things. So we'll stop there and just acknowledge people who did some of the work. None of it was done by me. Vivek and Aika are the people who did the work on the polyethylene and the polypropylene. The tire wear work was started by our joint MTech student, Vedant, and then Anit and Smita finished up that. And really glad to have physicist friends who would be willing to look at dirty tires and other chemical engineering collaborators as well. So thank you very much. I'll be happy to take questions.
Thank you, Guru. Let's have questions. We have 5 minutes. Questions? Questions, comments?
Rubber from tire wear, but like rubber is naturally occurring. I'm guessing they vulcanize it or something and make it. Is that what makes it a plastic, that process, or is it the?
So rubber is technically not a plastic because you cannot heat and reprocess it. So again, so you can have thermoplastics and you can have what are called thermosets. So epoxy is a thermoset. These are cross-linked materials. So all the araldite and M-seal and all of that is an epoxy. For the rubber, the natural rubber cannot really be used per se. A tire will consist of that rubber taken and cross-linked heavily using sulfur. That is the vulcanization process. And a lot of additives that you put into there, 30% of it is carbon black and so on. So in that sense, you can't heat it and reprocess it, but it is polymeric. So it is not a plastic technically, it's a polymeric material. Modern tires will comprise natural rubber. It will also comprise synthetic styrene butadiene rubber. But, if you're breathing that stuff, even if it's natural, it's not necessarily a good thing for you. So in that sense, it's bad.
Back to this, the tire business, are there engineering solutions that can minimize, yes, tires will wear out, but depending on the tire pressure, are there engineering solutions that can minimize the amount of wear or increase the lifetime over which the wear happens?
So, so this is getting into some detail. So this part, which is the large particles that get worn out, come from, depend on the condition of the tire, the condition of the road, those kinds of details. And there's ways of playing around with that, right? I mean, if I have this kind of a log normal distribution, by changing the road, by changing the way in which the pattern of the road is, or changing the tire, or changing the tire pressure, I can play around with some of these things. This part is a little more worrisome, right? Because if it's a power law, there is no length scale, right? And Shankar keeps telling me that means that it's hopeless, we are done for, because there's nothing I can change, right? That will give, because anything that I change physically, if there is a length scale associated with it, then I can change a material property and change this. This seems to be dependent on the weight that I put on this material and on the speed, right? Now, again, data that with the paper that I don't have here is that in general, all of this seems to correlate with the grip that the tire has, right? And that is correlated with sort of the slip velocity between the tire and the road. From a safety perspective, you want to have really good grip. And so in that sense, those are materials that are predisposed to wearing out more. So tire companies have spent a lot of time trying to figure out how to get the best grip without wearing the tire out. And there's some understanding around that. but all of this, the number of particles that come out, or the quantum of these smaller particles that come out, seem to be correlated with the grip that you get on this. So it seems like you have a catch-22.
But why would tire companies want to minimize the amount of wear? I mean, the more the tire wears, the more tires they sell. I mean, like light bulbs, right? They were engineered to fail.
Okay, let me put it this way. They've spent a lot of time understanding the wear problem. There's a lot of data in the literature on understanding the wear problem in rubbers, and also understanding grip, and also understanding, for example, things like efficient. So how do you minimize fuel consumption for per mileage and things like that? And that seems to correlate with how things grip the road.
So on the car and the road and same thing. So I got, I always thought the electric vehicles are all good, right? I mean, hydrocarbon and all. But now what you are telling me, like, tell us this. So overall, if I look at the hydrocarbon part, the carbon dioxide versus so has there been some kind of integrated calculation been made that which one is better? If he is not good, maybe we shouldn't go for that.
No, so the EVs, so what the EVs do is it prevents you from burning petrol and shifts that to a centralized power plant where you make electricity, and hopefully you can maybe even take that carbon and bury it and so on and so forth. So in that sense, it's a great solution to the problem of carbon dioxide levels in the environment. This is something which is new and that people haven't looked at, right? So this is a 2025 paper that we wrote, and what it tells you is that you've got these populations. Now people know that rubber wears out and you get these particles, but again, going back to the question of what is the implication of that? If this went into oceans and fish ate it and we ate the fish, yeah, that's a long way, and I don't eat fish, so I'm not too worried. But I do breathe, right? And so this really worries me, and this worries everybody, right? Because the fact that this stuff gets into the air and it stays persistently for a very long time. Yeah.
What was new there? The single fragmentation and the hundreds of
So
nanometer.
the fact that you get this
So that is not known.
This is not known. This is new, and we speculate as to the physics of why that might happen. But this data itself is something which was new. So this is the fraction as a function of the size. So it's just a size distribution.
Yeah. No, this is an earlier question. So the old piece road and this now concrete road is very much different. So in this distribution, how they are differ in these two cases?
So this part for sure will change. That we know. We've got data to show that if I change the road, this changes. This we don't think changes. We don't have a lot of data on that as yet. But our understanding is that this is likely not to change. The fact that you get, because what happens here is this is the sequential wear process by which you take the asperities on the road impact the tire, it forms a microcrack, those microcracks propagate and so on. This seems to be stuff that just gets torn off the tire, presumably. And that's why this seems to correlate really with the energy input that goes into running the tire. But we don't have enough data on that. So is this going to be different if I have an asphalt road versus a old tar type road? I don't know the answer to that.
I'm saying that concrete was is the hard and is more friction, old piece type, this is the more softened. So that does not matter?
I don't know. So for this, I know it does matter. For this, I don't know. Maybe Shankar has a...
There is a part of it, the one that you see long-term part, that...
Yeah, that matters.
This is like loading, unloading, how much. But the one that you get a power law, you still get a power law. The power law temperature could be different, right? But you get a power law. There are little that you can do about that. So if you look at any of your tires, you see your car tires, you don't drive the car, but look at the tires. You see there are parallel cracks on a tire. Those are the ones that are giving you the orangish thing. Those ones that chip off. this is sequentially, you're loading it constantly, see a part of the tire is going to be going down, dropping up every time that it goes inside. Those are ones that give bigger chips. But there is something which comes up from much smaller chips. We really don't understand what is the mechanism for getting these smaller chips. I mean, after the paper was there were a few papers, otherwise we would say, oh no, they had always thought that there would be this other power law, but that mechanism is still not.
So something like this, right? You look at this actually deforms quite a bit. And so basically you have this compression, decompression cycles that give you the cyclic wear, and that gives rise to this bit, right? So that, if I change the road, that changes. This, we don't have data. We don't think it should change, but we don't have data for that.
I was just wondering, is there a law? There seems to be an upper cutoff for the power law, but does it extend?
We don't know. Yeah. Yeah. So we don't know, right? Our aerosol counter goes to 300 nanometers. Of course, you know, it should at some point come down, but we don't know what that is. Maitri, the mic is not on. I think the mic is not on.
The sequential wear and what was the single fragmentation.
So basically,
are the stresses that give rise to one type or the other different? Meaning, is there something that produces sequential wear?
the stresses come from contact with the road and deformation of the tire. These are highly nonlinear materials that will extend to a large extent before they will encounter failure. And that's the reason that they're rubbery, right? So you can sort of stretch them a lot, and that makes their mechanics of failure especially complicated. Sequential wear is when you have this kind of a process where you have this compression and decompression, you're going to generate, there's always going to be a discontinuity at the point at which it peels off the road. That's going to generate these microcracks, and over time those microcracks are going to connect up. And in fact, this is this theory from this guy called Person, which says that these connect up, at some point they branch off and then they break off. And that's the sequential process by which you take this large thing and you sort of chunk it into smaller regions. Now that's not, we don't know really what happens here, but what we speculate is that this is sort of a direct, you just sort of pinch off stuff there, right? The smaller particles that come off. Is that related to the size of the carbon black in there? We don't know, right? But the mechanism seems to be something very different, which is why the distributions are qualitatively different.
So if you could show the collection of plots like this again.
Yeah.
So I just noticed that you probably don't have data to actually resolve that kink in some situation.
We don't. But this is basically, in some data sets we do, right? It looks like that same, so here we do, where we have lower speeds and lower weights, we don't have as much data. But it seems like the same log normal seems to fit all of that, right? We have more data sets than this. We have like 25 of these. Yeah.
So Jay, can you
go back?
Yeah, so there are several of these curves, right?
Yeah.
What do each of them represent?
Different speeds and different, so at each weight, we have different speeds, and then we have different weights. So normal load.
Yeah, could you go to that figure?
This one, right?
Right. No, the other one. So the one where we have some.
Oh, yeah, right. Sorry. This is the aerosol counter has different channels. So this is the 300 nanometer particles. This is the 10 micron particles. And there's, so we can look at the particles that come off in the 300 nanometer, 500 nanometer, 1 micron, 2 micron. So this is just so that's where we get the distribution from. So each of these data points is each of these channels. Sorry, I should have been clearer there.
Guru, I have a question. Yeah. So you nicely brought out this conundrum of the extreme utility value of polymers on the one hand, and on the other, potential serious one, not just environmental ecological, but potentially human health risk or even. So what's the recommendation? What are people talking about? What's the thinking at the moment? So the tires, I mean, you can't do away with that. I mean, you have to live with it. So what?
So tires, for example, so if you go back to IC engines, right, in the mid 70s is when catalytic converters came up, right? And the whole idea of catalytic converters is you're getting all this really, you're burning your petrol, but you're getting all this, NOx, so oxides of nitrogen and sulfur and so on, which are really nasty. So I'm going to do a mitigation strategy which is which is in situ in the car. So as it comes out of my tailpipe, we've got a catalyst, which is a rhodium catalyst, which is now converting that. Now, for tires, I agree, right? If you're going to make this, I can't drive slowly, or I can't, reduce my weight or reduce the weight of, in fact, with EVs, you're also carrying the weight of the batteries, which is typically an extra 500 kilos. So what I could do is then maybe come up with a way by which I can trap some of these. And we have some ideas around that. In fact, we have a joint PhD student working on this, which is to look at, is there a way by which I can figure out where the particles are coming out from and trap them in, right there in situ. So that's the only mitigation strategy I can see for this. Now for the plastics case.
Yeah, broadly, that's.
The broader case of plastics, I agree that at some point we'll have to be more judicious with how we use plastics. Plastics are incredibly cheap, right? And so we are also very blasé in how we use these things. We're very, very casual in how we use some of these things. Maybe if you recognize that there are health issues and that feeds into maybe some kind of.
So is there some emerging thinking as to which direction to take? Is this reduction of, plastic production the way to go? Yeah.
So this is a problem where commercial realities will meet, what is practical and what is implementable by national governments. The UN kind of the UN kind of agreements will always run into problems with plastics producers versus people who are essentially so there's always going to be sort of a disconnect between, let's say, a small island nation like Tuvalu, who's going to say, have the same vote, but now you have to stop producing plastic. This is going to be very difficult to do. So I'm not sure that is going to work, but there will have to be national level policies and legislation that will have to drive some of this. And that will come with the recognition that this is really bad. So if there's a health cost and it is impacting your healthcare system and your healthcare costs are going up, and that's what the government is spending on, they'll say, okay, maybe don't have so much plastic. So I'll put a tax on you. Or today they're saying we banned single-use plastic. Now that's not because of this, because those things are very often clogging our drainage system. There's no reason for it if it's disposed using, according to how they should be disposed. But that's our solution, is to legislate it. So eventually with some of these things, I think it's going to be legislation, right? Hopefully it is data informed, sensible legislation.
Hi. So this plot, this is the time versus.
Yeah. So this is the number of particles coming out. So the rate at which particles are coming out as a function of time. So I turn on my tire here, and then suddenly there's a spike. So before we run this, so the reason this entire thing is in this giant box, right? So we have this giant plexiglass box in which this is kept, is that there's so much dust everywhere in Mumbai that before we run this experiment, we have to clean up this thing, right? And so once we clean it up, that's my baseline level that I get for the aerosols. And then when I turn it on, it jumps up by typically about an order of magnitude. We let it run for 10 minutes and we do it for short time so that the tire doesn't heat up. So everything is done isothermally. And then when we stop, in principle, there's no place to go. So they shouldn't decay. But there's some quirks in why this happens, that there's a small decay. But notice that the 10 micron particles comes off, we stop the tire, it all falls down, and there's no more 10 micron plastics you can measure. The 300 nanometer plastics is going to stay in the air for a really, really long time. This is actually a couple of hours.
So this was my major question, like how they settle down depending on the size and mass of the particles, and
so this is
as well as like the effect of air drag and things, as well as like I expect the heavier particle to be, falling shorter, while the smaller particles, they are going to be travel much farther. So that kind of
this is really small particles, and they settle very, very quickly. These are 10 micron particles, and they're just dense. They settle. The larger particles, smaller particles do not settle. Now, do they go further away, or do they just get convected? Because these are so small, your Reynolds number is effectively 0. So these things, when they just convected, now the whole thing is in a box, so they can't go anywhere. What is actually happening is these things are charged and they're sticking on the walls. And that's why there's a small decrease. And there's also something about how the aerosol counter works. There's a small pump that gives rise to that. Now, in terms of how far do things go, the scary thing maybe just sort of. Yeah, so this is a paper that came out in 2020, where they went to a very remote national forest where you don't expect to see anything. There's no civilization for 1,000 kilometers around, and they found microplastics. So clearly, and these are not microplastics that are so small that you need an aerosol counter. These are big enough that you can look at in a microscope. So these were people who are trying to examine precipitation patterns. So they have these giant bins that they're sitting in the middle of a national forest, and plastics are falling on them. So even these kinds of plastics, and these are things like stuff that comes out of a paint gun and stuff like that, these get somehow convected over very large distances through some kind of atmospheric transport mechanisms, and even these end up. So the really small particles likely will go everywhere as well.
Last question, rather covered.
Amod.
First line of your concluding slide says that plastics are molecules held together by weak interactions. For physicists, the weak interaction strikes something that's
right.
But of course, I understand.
Right. So, okay, yeah, okay. Fair enough.
All right, let's thank Guru for that very informative talk. And please come over to West Canyon. Let's have some tea and snacks.